different but related topics. They are about using GNU Radio together with Python. At the beginning of these tutorials, I explained that GNU Radio can be used with Python. It can also be used with C++, but I guess most of you are more familiar with Python. And it's also a better language, I think, than C++ for doing things interactively, for prototyping things quickly. So we will be looking at how GNU Radio can work together with Python in two different ways. The first of them is this scripting tutorial, which is about how we can do a flow graph in GNU Radio Companion and then call it from Python or just run it. And the main application of this is to conduct observations because say you want to do some kind of real radio astronomy observation. You are probably going to be observing different targets. You might have some calibration targets. You might have some science targets. Or if you are doing a SETI search, you might have like your on and off scans. So those are different targets. You usually want to do something to get on target. If you need to move antennas, you might as well do it from Python. So you might call some Python code to move the antennas to the target. Then there might be additional systems you need to set from Python. I don't know, LNAs, gains, frequencies, which doesn't have anything to do with GNU Radio. And then you might run something in GNU Radio for data recording, real-time data processing, or something like that. And more importantly, if you have a list of targets you want to go through, and maybe also some time intervals, you essentially need some kind of code. You need some kind of for loop to get through all those targets in an effective way. And for that, a programming language like Python is good because you can write for loops. Something which is graphical as a flow graph as GNU Radio is not very good if you want to express repetition or iteration as in a for loop, for example. So I think that scripting GNU Radio flow graphs using Python is a good way to combine both approaches. Use the flow graph approach for what is good, and then use Python to wrap everything up and drive it. So that's the first thing we will be doing. And the second thing is embedded Python blocks. So there is a functionality in GNU Radio where we can put a block in the canvas and then we can write the Python code which that block is going to run. And that's a very good way for prototyping signal processing algorithms. If you have some calculations in mind you want to do, then embedded Python blocks are good for that. And I will be demonstrating that by showing how to calculate the spectral kurtosis, which maybe some of you are working with because it's a common interference detection metric. For example, it's quite commonly used in astronomy for interference detection. So all of this said, let's get started. I have GNU Radio Companion, and I already have the flow graph in the scripting folder open. This is all already in GitHub. And I'm going to go through all of these because most of the blocks we have already used. There are a bunch of parameters, so I don't want to do this flow graph from scratch. So I will be going through it and explaining. We have the RTL-SDR source. So both of the tutorials today will be using the RTL-SDR. Same settings as usual, the sample rate 3.2 mega samples per second. That means we are looking at 3.2 megahertz of spectrum. The frequency 98 megahertz. And this is a parameter. I will explain shortly what a parameter is. So recall 98 megahertz is the FM broadcast band, and there are some FM radio stations. So that's a simple band where we have some signals we can easily see, even with a small antenna, and it's good to run some tests. So what is a parameter? So far we have been using variables to set values and also the GUI entry, which is something that will let you dynamically change the value of a variable by entering a value on a field on a GUI. But there is also a parameter. So when we want to interface a flow graph with something that calls the flow graph, whether that's a command line interface as bash, I mean the command line as here, or whether that's some Python code, which is going to call the flow graph. Then we have those parameters, which are values that get passed into the flow graph. And they can have default values, so we can look at how this looks like. The ID is the name of the variable. We will use that same ID throughout the flow graph where we want to use that value. So I have frequency in here, and that's the way this parameter and this field in the RTL-STR source are linked together. Then we can have a label, which is human readable for documentation. The type, as usual, we have complex float, integers, string also. A default value, which is used if the parameter is not set, and it is optional. And also a short ID, which is used to generate a short command line argument. So what parameters do we have in this flow graph? Let's see, we have the frequency, which is the R frequency we tune the RTL-STR at. We have an observing duration, because also something different about this flow graph compared to other flow graphs we have seen is that this flow graph runs for some time and then finishes. And this is something that GNU Radio does on its own. So by default, any flow graph will keep running forever because there is nothing which says, hey, the flow graph is finished, nothing more to do, stop. But there are some things that can cause a flow graph to be finished, and so it will stop. The most obvious of them is when we are using file source. If we don't set it to repeat, so if you remember, there is the file source, and there's a repeat parameter, which says whether we want to play the file multiple times in an infinite loop or whether we just want to play it once. If we set repeat to no, then the flow graph will stop. It will read the whole file, do whatever processing we have described, and then finish. And that makes sense for doing some data processing on a file. There are other ways of making a flow graph stop. For example, there is this head block, which means only let go through the first number of items here. So we have a formula, which is the sample rate multiplied by the duration. This is this parameter. And then we round because either of these could be a floating point number, and we need an integer here. So the result of that calculation is 32 million in this case. And what this head block is going to do is it will let pass the first 32 million samples, and then it will say, hey, I'm done, I'm finished. And what GNU Radio will see is because this block is not going to produce any more output, then all of these will not do anything else because there is no more input to run all of these. So at this point, the flow graph does nothing else to do, and so it's finished. So that's how we control the runtime of flow graph, and it makes sense for many kind of radio astronomy observations because we want to conduct the observation for a certain duration. So that's what this parameter and the head block is all about. Then let me show you the rest of the flow graph because the parameters will make more sense. So what we are doing is we have GUI frequency sinks, but these are disabled. Remember that I can enable or disable a block like this because since this block is intended to be called from Python, it will not have any GUI. And I will explain how to do a flow graph without a GUI. There is an option in here, no GUI. Well, I can explain it now. So until now, we have used the Qt GUI option here in generate options. And that means that the flow graph is going to have a GUI. Whenever we run the flow graph, it will have a window. Maybe there's nothing in the window if we have no frequency sinks, no entries, but it will have its own window. And we can add this frequency sync or any other number of displays to the window. But there is also no GUI, which means this is a command line application. It will not have a window. It's intended to be called either on the command line or from some other code. And there are the options prompt for exit or run to completion. Run to completion is more common. It means run until the flow graph is done, as I was describing. And we can see when we set this to no GUI, then this becomes red. And if I go to the yeah, to the flow graph errors, it says can generate this block in mode no GUI, and that makes a lot of sense because we can only have GUI blocks when the option is to have a GUI. So this needs to be disabled. This was just for testing. What else do we have? We have the frequency translating FIR filter, which is doing a decimation by 16. It's basically selecting 200 kilohertz of bandwidth somewhere within the 3.2 megahertz of bandwidth that we are receiving. And this is configurable. So there is a parameter here which says frequency translating frequency. And it is currently set to 800 kilohertz. So this is the 800 kilohertz. What that means is here we are selecting something which is at 98 megahertz plus 800 kilohertz. So that's 98.8 megahertz, which happens to be the frequency of an FM radio station. This is selecting a single FM radio station. And this is just for the sake of the example. It's just so that we have something we can control with the parameter and then see the result of changing that parameter in the output we produce. What do we do with this single FM radio station? There is this SIGMF sync. This is very similar to the file sync. We have used file sync before to record some data. The main difference is this uses the SIGMF format, which I will explain sometime later. It's the same as the file sync, but there is an additional metadata file, which is in JSON format. So that's plain text. It is human readable and contains information which is important to make sense of the file, such as what is the data type, and also the parameters we are passing here. So what is the sample rate? What is the center frequency? You can have an author, you can have a description, you can have which hardware was used to record, and you can have much more metadata in SIGMF, which is not supported by this block. And as you can imagine, that can be quite useful because if we are doing different recordings, then to use them, we will need to know the sample rate, the frequency, and maybe some other metadata. So SIGMF is a very good way to keep track of that information. We will look at the output file when we have some output files. What else? There is the file name. So IQ file output. In order for us to select where we want to write this file, there is an IQ file output. And by default, I have this to /dev/null. In Linux, at least, I don't know if this works in Mac OS. Maybe it does because it's also Unix. That means write to somewhere which is discarding all the information. It's good for testing. If we don't want to generate an output file, then we leave this default value of the parameter and it will just write nowhere. But now that I'm remembering, maybe this default doesn't work properly with the SIGMF file sync because it intends to generate two files, two separate files. But anyhow, we will see that. What else is in here? Basically a spectrum calculation with the FFT. We have already done this a number of times, string to vector, FFT, complex magnitude squared, integrate, and integrate depends on integrations, which is a variable. Where is it? Here. Well, here I have integration in seconds, and then I compute my number of integrations as we have done before. So nothing mysterious, and the FFT size 65,000 points, which is good to have a fine spectrum resolution. What are we doing with this spectrum? We are writing it to two different places. There is a file sync where we write the vectors. In order to write vectors, we need to set the vector length to this NFFT parameter. Otherwise, if this is just one, if this is just one, which is the default value, then this is like lighter orange, meaning the vector size is one, and we get red here because it's an invalid connection. So we need to set the vector length to the correct value. So this is fine. This will write a file with the spectrum data, and we will be able to load it with any application we want. But I also want to demonstrate something which is called a vector sync. When we want to pass data between GNU Radio and some other code which is calling it, such as Python, it's not necessary to write files. We can use the vector sync, which will store some information in memory, and then we can read from that memory of Python, and we will see how this looks like. It's often more convenient than generating a bunch of files. The reason this is called vector is because it uses a C++ vector to store the data. So that's not a very fortunate name because it might be confusing with the vector length. This vector sync can be used for a vector of one element, or it can be used for a vector of any length, and it will store as many samples as we feed in of that vector. It says it's going to reserve memory from some number of items, which by default is 1024. But if we put in more items, it will keep reserving more memory. So this works automatically. The only thing you need to do to know, sorry, is you send in data, and then there is a way to access that data within Python. So what else? Let me see if I have explained all the parameters, the two different output files, and these variables for the FFT. Yeah, I think I have everything. So any questions about this flow graph? I think it's something very familiar. It's mostly what we have been doing up to now. Okay, so something I can do with this flow graph, usually we have been pressing this execute the flow graph button. There is also this generate the flow graph, and it says I'm generating a Python file. You can see here there is a Python script, and I can go back to my terminal. And if I list the files here, I can see there is this RTL SDR receiver flow graph, which is a Python script. And I can run it with help. And we can see this is like a command line tool application. It's a Python script that GNU Radio Companion has generated for us, but it has command line tool arguments for all the parameters we have in the flow graph, and it has help. And in the help, we can see the descriptions we have put. So for example, the duration, this comes, observation duration is the label we added in here. So that's the reason we have it. And then it says what the defaults are. So if we want to run this, then we can specify all of these. So for example, I could say duration, 5 seconds, the frequency translating FIR filter, 800 kilohertz is fine. And the frequency is also fine, 98. So maybe I do not want to change those. File output, then, I don't know, test IQ, and then spectrum, file output, test spectrum, something like this. And you can see we can run this, and it runs like a command application. It prints some login. This is something that the SIGMF data sync generates. It says, I'm generating the metadata file here, and I'm writing the data in here. Because, as I explained, SIGMF is composed by a data file, which is exactly like the files we have been writing with the file sync, and a metadata file, which I will show you in a second. And this has run for 5 seconds, which is what I said here. So nothing very surprising. I can show you that I have the 3 files this is supposed to produce. So the test IQ, SIGMF meta, test IQ, SIGMF data. Something nice about SIGMF format is that it can be open with different applications that support it. For example, there is an application called InSpectrum, which is nice. I don't know if it's included in Radio Conda or not, but it can be installed independently, definitely. And we can open one of these files. It doesn't matter which, because InSpectrum knows that the two go together as a pair. So if we do that, then we can see the spectrum of the signal. So this is frequency. We can see from minus 100 kilohertz to plus 100 kilohertz. This is the 200 kilohertz which have recorded because of this frequency translating FIR filter. And then let me put more reasonable settings here. So we see the FM radio station. Its shape on the spectrum is changing because the music is changing. The duration is 5 seconds. So nothing too surprising. And something else we can do within Spectrum is some really simple signal analysis. I'm going to show this very quickly. So we can add a plot for frequency, and then we can drag it like this. And this is the frequency of this signal, the instantaneous frequency. And we can zoom in, and then we can see how the frequency is changing, basically following the audio signal on the FM waveform. So in Spectrum, it's quite a useful tool. We can remove this plot like this for looking at SIGMF files we have recorded with either GNU Radio or any other application. Another useful application, this actually runs in the browser. It's called IQ Engine. So you can go to iqengine.org, and then there is a catalog of recordings. You can see, for example, there's a GNU Radio CMF repository, which is where I'm at. And there are examples of many recordings, like a microwave, and we can open them. Let me see, microwave. Can I open this? Yeah. Yeah, it's somewhat slow because it's loading all of these remotely, but there you go. This is a microwave, and it will keep loading. But more interestingly for us, it supports a local file pair and also local directory. If you are using Google Chrome, I'm using Firefox here, so this option is not supported. But the file pair works fine, so we can select the SIGMF data and SIGMF meta. And then we can see it's basically the same thing we saw in Spectrum, but it's on the web browser, so we don't need to install anything. Okay, so that's IQ Engine. Any questions so far?
Daniel, for folks that might be interested in downloading some of these samples, if they're looking at their own data from the telescopes and wondering if certain signals that they're seeing match the morphology of the signals that you have in these examples, there are tools available, I think, to convert SIGMF into the file formats that we typically use.
Yep. So I think there are tools to convert from SIGMF or either from the raw data file into something like a polyphase filter bank output, and then you could run raw spec on it, and then you could do turbo SETI or something like that. So definitely that can be done. In fact, on some of the previous years, I don't remember which ones off the top of my head, I have done something like that. I have showed how to write GUPI files from GNU Radio. So you can open one of these CMF files in GNU Radio and write it as a GUPI filter bank file. That's one of the ways of doing it. And certainly all of the files which are in here, you can download the data and metadata files. So that's a good way. For example, if you are seeing something you think might be cellular, then you can download this one and you have an example and you can compare and you can convert the data file to any format you need.
Thanks.
Other questions? Okay, let's move on. So the next thing I have here is how to call this from Python, because we have seen how to call this from the command line, but the intention is to call it from Python because we want to write something like an observation. In here, I just have my RTL-SDR. I don't have anything like a real telescope. So this is going to be a simulated observation rather than looking at different sources on the sky. We are going to look at different frequencies where we will find different signals. And that's the main parameter we are going to control. But the same principles apply if you want to observe at different sources, if we are conducting an observation with a telescope, and in a couple of weeks, when we are at the Allen Telescope Array, we will see how the Allen Telescope Array can be controlled in Python. and you will have a clear idea of how you could run the allelotropy array and at some point have GNU Radio in there capturing or processing some data. So the way I want to go about this is with a Jupyter notebook. I have this receiver control Jupyter notebook. And I like using Jupyter because it's quite good for interactive coding and also for visualization. And I already have written all of this. It doesn't make sense for me to write this in real time, but I'm going to go slowly through all the code so you can understand how it works. First, I'm importing some basic packages you might be already familiar with. Pathlib is included in Python. And then we have NumPy and Matplotlib. And here the important thing is we have this RTL-SDR receiver flow graph, which is this, let me see, let me put this also to the background. So this RTL-SDR receiver flow graph.py, I can import it in Python. And we can even look at it, look at how it works. So let me open it with a text editor. Let me see, this is scripting. And this is the Python file which was generated by GNU Radio. Maybe something like this is fine. So you can see there is a class. I showed something like this on the first tutorial on the introduction. And this class is going to be our flow graph. And then if we run this as a command line application, there is a main function, which is what is going to be running. So that already gives us a clue about how to run this from Python. The thing we want to do is to import this RTL-SDR receiver flow graph class from the RTL-SDR receiver flow graph Python file that GNU Radio has generated. I'm setting some parameters for figures because I like them to be this particular size. And the first thing we want to do is we want to know how to run the flow graph. So this is equivalent to calling the Python file from the command line, as I did before. And the thing we do is we instantiate the flow graph class. So we call RTL-SDR receiver flow graph. Then we can pass parameters. So we can specify duration, we can specify the IQ file output, and the other parameters, they will have the default values because they aren't listed here. And we assign this to a variable, which is normally called fg for flow graph. And this is going to be our flow graph. Usually the only thing we want to do with the flow graph is to run it, which is called flowgraph.run. And this will run the flow graph until it finishes. Let's see, I think I need to evaluate this cell, and then I can evaluate this one. And this will do exactly the same thing as we have done in the command line. It's printing out the same information. And it has run for 3 seconds. Now you can see the cell is finished. And the same, it says I'm generating these output files. The second thing we want to know is how to access the information in the vector sync, because remember the spectrum data, I had sent it into this vector sync and I said, this is accessible from Python. This is a good alternative to generating files because you can read the data from Python directly. So question is, how do we read that data from Python? We can see that within the flow graph, each of the blocks we have, they are present. So for example, we can call up this flow graph spectrum vector sync, and it will say this thing is a block vector sync, which is how in code or in Python, this block is actually called. Something important is we need show all block IDs. So blocks have, all of the blocks have IDs like these, blocks file sync 1. And that is the name of the member we need to specify here. So that's how we can select each of these in Python. And then we can edit the IDs. I could type any. And this one I've changed because by default there are numbers like 0, 1, etc., so that it doesn't repeat. If you are going to use the ID for something, it's good to change it. And then you have something which is easier to remember. So I have spectrum vector sync, and that is much easier to remember. So spectrum vector sync, just because this is the ID I have set in GNU Radio, is my block. Then how do I tell the block, give me the data? As usual, there is documentation, and I have the links in here. So there is documentation on the wiki for vector sync. And look at it, it's actually pretty good. It has an example, which is similar to the one we are using, about how to use this in Python. There is the flowgraph run, as I had, and then we are flowgraph, the name of the sync, dot data will give me the data. So usually the documentation is quite good. If the thing you want to do with the flowgraph is not in the documentation, then oftentimes there are these header files which are also linked in the documentation sometimes. In here it says to do, but for some other blogs there are links. And you can search for this. If you go to the source code in GitHub and go through the list of blogs, you can find the blog you are interested in. So you can see that there is this data. There is also tags. I'm not going to explain what tags are, but they are a way of assigning metadata to samples in GNU Radio. And there is also reset, which clears the data which is stored in this vector sync. So this is a way in which you can figure out the operations you can do with a certain block. Maybe, I don't think I have tried this before. Maybe also calling help in Python works. I don't know. Let's see if it works. Yeah. It also tells us it supports a method which is called data, reset, and tags. So that's also something you can use. But you need to be careful because since this is a GNU Radio blog, it also has a bunch of other methods which all the GNU Radio blogs have. And normally we don't need to call them directly. So, okay, we can grab the data by calling fg spectrum vector sync dot data. And this returns a list of numbers, as you can see here. That is not particularly nice. So what we can do is to convert the spectrum sync data to a NumPy array. That list of numbers we convert to an array. And then this is supposed to be an array of vectors, remember, because we are storing the FFTs in here. And each of the FFTs has 65,000 elements. So it would be nice to see this list of numbers as a matrix, which has however many rows it needs to have. That depends on the length of the observation, because this is like the time axis. And then as many columns as the FFT's shape, which we can grab from fg.nfft, because any variable we have, where is my NFFT variable here? So any variable we have is also accessible in this way. So that's a good way. What I haven't mentioned, but should be mentioned, is that if we do any changes here and then click on generate the flow graph, then this is going to generate a new Python file for us. And then if we rerun all of these notebook, like restart and run all cells, we will see the modifications here. So that's a good way to iterate and make changes both in GNU Radio and in the notebook. So we are reshaping the spectrum so that it has the correct shape. And then we have two rows that corresponds to 2 seconds worth of data. Remember, my integration time is about 1 second. And we have done an observation of 3 seconds, but I only have 2 seconds of data here because maybe the integration time is slightly larger than 1 second. So with 3 seconds of data, we only get 2 FFTs rather than, or 2 integrated FFTs rather than 3. So that's the reason the shape is 2 times 65K elements. And then we can do some plots. So this 10 times the logarithm 10 is to convert to decibels. And this is the data. You can see the FM radio stations. This is the one we are interested in, and there are a bunch of other radio stations. So that's a good way of getting data from GNU Radio into Python without having to write files in GNU Radio and then read files in Python. Any questions? Okay, something important is that the flow graph continues to exist. So it's finished because I called run and it finished. But the flow graph still exists. That's the reason I can interact with all of the elements in the flow graph. But something else that happens is that the flow graph also has access to the RTL SDR. So if I try to use the RTL SDR for something else, like for example, running the flow graph from the command line, then I will see an error which says the something like USB claim interface error -6. That means the device is busy because the flow graph I still have here has opened the RTL SDR. We need to delete or destroy this flow graph to release access to the RTL SDR before trying to use. We delete the flow graph. This is deleting a Python variable. And then we can do something else with the flow graph. So we can use it from here. Let me do a very short duration to show that deleting the flow graph in Python already releases the RTL SDR. So this has finished successfully. Okay, what I want to demonstrate is together with all you know so far, which is how to conduct something that looks like an observation by doing a for loop in Python and then calling that RTL-SDR receiver flow graph at some point in the for loop. And as I mentioned, I don't have a telescope here, so we are not going to point to different sources on the sky. We are going to use the RTL-SDR to tune to different frequencies where there are some signals of interest. So I know in all of these particular frequencies, there are some signals to be found. And these are the RF frequencies. So these will be the center frequencies for the spectrum. But then we have the frequencies for the frequency translating FIR filter. So what happens is at each of these offsets, there will be an IQ recording of 200 kilohertz of spectrum. So for example, at 98.8, which is one FM radio station, at 95.8, also because 95.5 plus 300 is 95.8, at 117.3, also, etc., etc., with all of these. And we will then see how these signals look like. I'm going to use a duration of 10 seconds for each of the observations. And I'm going to keep collecting the spectrum data in Python. I'm not going to write it to any files. The IQ data, yes, I'm going to use the CGMF file sync to. I will just handle it in Python because later on we are going to plot it. I'm going to create an output directory for this observation, just temp observation. We create the directory, and then something really simple for each RF frequency in this list, and for each frequency translating frequency in this list, I'm going to print a message saying that I'm going to receive at that frequency. I'm going to generate a file name, which is the output directory, IQ data, and then my RF frequency in megahertz. So that's how I will end up with different file names for each of the observations. We could have a number like 0, 1, 2, 3 in here. It doesn't matter. Then I'm going to instantiate my flow graph with the duration of 10 seconds I have here, the RF frequency coming from the list, the frequency translating FIR filter frequency coming from this other list, and the IQ file coming from here. And if we were controlling a real telescope, somewhere in here, move antennas, set up LNAs, etc. This would be the moment when we want to do all of that. And when the telescope is already on source, then we run GNU Radio. So, and then we access the spectrum data just as before, and we save it in this dictionary indexed by our frequency so that then we can do plots of all of these data collections. And then very, very important, before running the next loop iteration, we need to delete the flow graph because otherwise this will run and say, hey, the RTLSDR is claimed by the previous iteration, so I cannot use it. And let's run this. Maybe I want to put this somewhere here. Let me actually hold it up so that it has better reception and I can run this. And while it runs, it will take, I don't know, like a couple minutes to finish. Any questions or comments? Okay, let's give it some time that it needs to finish. We can see that it's doing the second, and now it's doing the third.
Is it reopening the device each time it's doing this, or staying
Yeah,
connected?
yeah, it is reopening the device. So each time that it is running, it is starting a radio from scratch. And so there is a little bit of delay because it takes like a couple seconds to open the RTL-SDR. There is another way of doing all of this, which is run the flow graph just once, but control GNU Radio in such a way that we start and stop the flow graph. Rather than running it and deleting it, we can stop it, resume it. So what we can do is we stop it, then we reconfigure the flow graph to change the frequency and to change the output file name. And then we can resume the flow graph. And if we do that, then we are not reopening the device every time. So we save like a couple seconds in this case for each of the observations. But it's slightly more tricky to code it. So that is, which is the most basic approach. Okay, so this is done. I see that it's finished. The last frequency was 1090 megahertz, and it is here. So what can we do with all of this? Remember that we have saved the spectrum data into a dictionary. We can see what's on the dictionary, and not surprisingly, there is for each of the frequencies a matrix with shape 9 because we recorded 10 seconds, but as I mentioned, the last second doesn't make it to the spectrum, probably because each line is slightly longer than 1 second. 65,000 points of FFT bins, and then some numbers. What we want to do with all of these is to plot it. So here is some plotting code. Probably you have similar plotting code in the work you are doing. So I'm going to go through it really quickly. The plot I want to do is something like this. So we are showing the spectrogram or waterfall, which is basically time here, frequency here, and by the color. And then we also show the spectrum, which is frequency here and power here. And this is an average of the recording over the 10 seconds. If we wanted, we could also do like a maximum or some other statistics. We could have multiple things in here, like the maximum, the minimum, etc., etc. But the average is good for the example. We do this very quickly. For my frequency axis, I need to compute the frequencies of the frequency bins with FFT frec. Then I need subplots because I'm going to have these two plots. The waterfall is, let me see. Oh, okay, I see. Yeah, because the waterfall has 65,000 frequencies and my screen doesn't have 65,000 pixels, it makes sense to reduce the frequency dimension of the waterfall by grouping FFT beams in blocks of 64 and then taking the maximum. That gives us a nicer image than trying to plot something which is 65,000 pixels wide, because then Matplotlib will try to do some interpolation and it doesn't work as nicely as doing a max, which is what I'm doing here. I'm doing this reshape to group things in groups of 64 frequency beams and then doing a max across the last axis. So that's just for nicer results visually. ImShow, I'm showing the waterfall in dBs and setting the extent so that everything is nice. And then plotting the average of the waterfall data over the axis 0. And in this one, I'm really using the 65,000 frequencies because there is no problem to plot 65,000 elements. And that's it, some labels. And we iterate. So we do this for each of the data sets we have produced. So we can see at 98 megahertz, we have some FM radio stations. At 95 megahertz, we have other FM radio stations. And there is this one which is quite strong. Then 117 megahertz, we can see a lot of interference, but there is also signal here which I showed already on the first tutorial with GQRX, which is an aircraft navigation signal. It is this one here. Maybe we can look at it with the IQ recording better. At 420 something megahertz, there are some handheld radio signals. So this is called Tetra. It's used by police, fire department, etc. They used it for the handheld radios they have. And all of this is encrypted, but the signals are strong, and that's a good signal to test that we are receiving something. What else? So some cell phone signals around 800 megahertz. The main signals are very wide. They are 10 megahertz wide, so I can only see the edges here. But there is a smaller signal, which is for IoT devices. So there is this 180 kilohertz wide signal. What else? 935, more cell phone signals. As you can see, these days, everyone has a cell phone and everyone wants higher data rates on the cell phone. So the spectrum is full of different generations of spectrum signals. And this one is GSM, which is the first cell phone generation, or not the first, but what is known as 1G. There are previous generations, but they are so old they don't even have like 1G, 2G, etc. So GSM, 1G. And then what else? At 1090 megahertz, it is not possible to see in here. The things we see are interference, but hopefully there are some aircraft position signals in here. There is something known as ADS-B. I think I mentioned this on the first tutorial, which is aircraft beaconing their own position. And that is how you can get those online maps showing aircraft in real time, or applications on your cell phone. They have a network of 8. So those are the signals. Let me try to take a quick look at what we have in here. So in temp observation, we have created SIGMF files for each of the data sets, or for each of the frequencies. So for example, we can look at one of these IQ data, sorry, temp observation, IQ data, 1090, SIGMF data. Yes, and you can see some pulses here. Showing pulses sometimes it's tricky because we have this zoom to zoom in time. We have the FFT size, which also affects the frequency resolution. But you can see all of these pulses. They are transmitted from aircraft and they are used to encode the aircraft position and other data. And that is how you keep planes from crashing onto each other on the sky. That's the main reason why the system exists, so that other plane can display in real time the positions of all the other planes. But you also get these applications or online maps showing aircraft positions. What else I wanted to show here? Let me see if there's anything which is worthy of looking at within Spectrum. Yeah, I said this 117. So 117. Yes. So you can see in here there is the main signal. There is a Morse code ID which is transmitted every 30 seconds or something like that. Since the recording is 10 seconds long only, we don't see it because it was transmitted at a different time. But we see these sidebands in the signal, which are a sine wave. They're actually a sine wave. So this is frequency modulated with a sine wave. And that's the reason we can see a sine wave. And this is how the aircraft knows the direction in which the station is. This is a radio station located on ground. And this is a method that aircraft use to navigate on the sky to find their position, to find where to go. And it's an older system. It's way before GPS existed, and it's still in use because GPS it's not extent of problems. Maybe you have heard that there are GPS jamming and GPS spoofing, where people broadcast other signals the same frequency of GPS, and then GPS receivers cannot function properly because they cannot receive the real signals. So this one still in use, still quite useful. It's called VOR, which means VHF omnidirectional ranging, I think. So what else? I want to show how the SIGMF meta file looks like. So you can see that you could use it manually, even if you need it. So there it is JSON. And then you have things like data type. This means complex floating point 32 little endian. The sample rate 200,000 samples per second. Version of the SIGMF specification, and these are the parameters I had set on the SIGMF sync. So we have all of them here, and the frequency. And you could also have a timestamp here, the UTC timestamp for the beginning of the recording. That's also something very useful to have. So I think that's it with this part of the tutorial. Any questions about all of this? So the next step today, I'm going to show you how we can write embedded Python blocks. That's a way of inserting some signal processing code written in Python into GNU Radio block. And whenever you have some algorithm that you want to try out, especially if you want to run it in real time, that's a very good use case for the embedded Python blocks. As an example, I'm going to use the spectral kurtosis, which is, I'm going to explain it very briefly in a second. It's a statistic or a measure that can be used to determine when something is Gaussian or something is not Gaussian. And the main reason why this is interesting in radio astronomy is because random noise is Gaussian, and other kinds of signals, such as interference, are usually not Gaussian. So by calculating the spectral kurtosis, you can tell whether something you are seeing is noise or perhaps interference. And so it is used for interference detection and cancellation. It is also used in many SETI pipelines. Maybe some of you are already working with something that uses spectral kurtosis. So that's the reason I wanted to use this as an example. For those of you which are not familiar with spectral kurtosis, that's a formula we will see now. Personally, this is not a concept I often use. It's something which is more often used in radio astronomy than in communications signals processing, for instance. There are different there are slightly different definitions of the spectral kurtosis. So I'm going to take one from this reference paper, which is the paper I have in here. I found it online, and it's a good self-contained and brief introduction to all of these. And basically, it gives you the formula for an unbiased estimator of the spectral kurtosis. So the thing we are doing here is we have computed an FFT with m points, and we have actually computed a series of them. So we have m different FFTs of n points each. And those are denoted by xi, that's the ith FFT, and m is the FFT bin. M is just the frequency here. And what we do is this formula. So it's essentially like raising all of these to the power 4 and doing an average of the power 4 and then comparing that with the average to the power 2, which is the variance. So it's a comparison of the fourth moment and the or quotient of the fourth moment and the variance, which is the second moment, if that tells you anything. Anyhow, the exact formula is here. We have the complex modulus, we have the power 4, there is this m plus 1, m is the number of things we are adding. There is here like this, and then we need to subtract 2. And then we have this factor in here. And basically, these are the numbers that give you an unbiased estimator. There is a formula which is like this, but if you want to run this as an estimator over a finite sequence of m observations, then you need like these correction factors. It's like when computing the standard deviation, you divide by m minus 1 rather than m. What properties does this have? So for example, it says the spectral kurtosis of a complex random variable is 0. So with this normalization, we get 0 when things are Gaussian. It also says when there is a deterministic signal, basically something which has fixed amplitude and frequency, then the spectral kurtosis is -1. And it doesn't say about other signals, but we will see that other kinds of communication signals tend to have positive and large spectral kurtosis. So we want to compute this calculation in GNU Radio. And we could do it without embedded Python blocks because GNU Radio has blocks for basic math operations. So it has blocks for calculating the modulus of a complex number, for multiplying things, for division, for addition. So we could write a lot of blocks which perform this calculation, but that would be confusing. We want a single block which does this calculation. So this is what we are going to do today. In GNU Radio, I have basically the same thing as every time we use the RTL-SDR 3.2. Sorry, I was making this before and did this wrong. So 3.2 megasamples per second, a frequency of 98 megahertz. And if we run this, we see the usual FM radio stations. I have some low averaging on the FFT, so it's nicer to see. And then we want to compute and plot the spectral kurtosis of these FM radio stations. And for me, that is a good thing to do because I don't have that much intuition about spectral kurtosis. So being able to see in real time how the spectrum looks like, how the spectral kurtosis looks like, and being able to change frequency and look at different signals with my RTL-SDR gives me a better understanding of how spectral kurtosis behaves when you give it different signals. So that's like a bonus of doing this exercise with the spectral kurtosis. Okay, so what do we need first? This calculation begins already with some endpoint FFTs. So let's do that. we know how to do an FFT. We need a variable for the FFT size. So nFFT, then stream to vector. nFFT, then FFT. Where is that? FFT. nFFT here. We can use any window we want. And then the output we have in here is the xi's in this formula. Okay, any questions at this point? Okay, the next thing we want to do is to put a Python block. And we are going to put it in here and to connect it right away. At the moment, this is an illegal connection because we haven't set the data type we want, but we will do so. So embedded Python block. When we double click, there is code. This is the Python code corresponding to the block. And there is opening editor, choose editor, depending on the operating system. This choose editor might work somewhat differently. For me, I already have my text editor configured, so I can do it like this. And as you can see, this comes already with a template. And there are detailed comments in the template. So it explains that every time that this file is saved, GNU Radio will update things here. So that is very convenient. And it basically gives you all the details of how to write this embedded Python code, Python block. By default, it is multiplying the input elements by a parameter. So there is an example parameter, which is declared here. There is example parameter. It has a default of 1. It is saved here, and then it is used here to multiply the input by this value. And you can see the parameter example param is here and can be set. So this is how the template looks like. We are going to modify the template. And the first thing we are going to do is to change the name. This is the name. So spectral kurtosis, and we can save. I've saved it, and we can go back. And we see now the block is called spectral kurtosis, and I can even close this because it will keep refreshing when I change the code. So that is good. The next thing we need to do is to declare what the signal types are, because at the moment we have NumPy complex 64, so that's the blue thing. And that is for both the input and output. But there are two things we need to change. The input needs to be a vector, and the output also needs to be a vector. And the output needs to be a real number rather than complex. If we look back at the formula, these xi, they are the FFT output, so they are complex numbers. But then, because we are taking modulus, all of these is a real number. So how do we do that? Vectors are declared like this by writing in a tuple the data type and the number of elements. So let's write it like this, 4096. And then I can see this becomes dark blue, and now I can make a connection because both of them are 4096 elements in the vector. This one's still blue because I need to set it to real, so that's float 32. And I believe these data types that you can use are documented somewhere. What is the correspondency between NumPy data types and GNU Radio data types? And for the output, I also need 4096 elements because let's look again at the formula. My 4096 elements are this little m index. So my spectral kurtosis is also going to be a vector of 4096 frequency pins. So that's it. This is converting complex numbers in floating point numbers or real numbers. Do we need any parameters? Well, yes. If I look again at the formula, there is one parameter we need, which is m. the number of things we want to sum up. So I'm going to put here m and give it a default value of 10. It doesn't really matter. And I'm going to save it here because something important is there are two functions we are interacting with. There is this init method, which is the constructor. This runs when the block is created in GNU Radio Companion. And then there is the work function, which is called periodically, and it receives some input samples, and it needs to calculate the output for the corresponding output samples and write the output. For example, in here, we are multiplying the input samples by this parameter and writing that as the output. So to access variables which are in here from this function, we need to store them somewhere in self. If you know anything about Python classes, that will be more or less clear why. If not, well, this is a class, and to share data between this function and this function, we store data in the class, which is represented by this self variable. So that's the way to explain it. What else do we need to do? We need to do something else with the block definition itself before starting to write math in here, because something about this formula is that it works in blocks. So you can imagine we have our FFTs. This is going to produce an endless stream of vectors. So we have one FFT, the second FFT, third FFT, etc., etc. And we want to make groups, for example, groups of 10 of those FFTs. Here, M equals 10. We make those groups of 10. We calculate that formula, and that produces a single output, which is the first spectral kurtosis. Then the next group of 10 comes in. We do this calculation, and that's the second output. So the spectral kurtosis calculation is reducing the data rate by 10 because it's making groups of 10. More in general, it's doing a data rate reduction or a decimation by a factor of this number m. It is very similar to this integrate block in that respect, which is applying a decimation of 49 in this case. The integrate block is just doing one of these summations. It's doing like summation, and that's it. Our spectral kurtosis block is going to do something more complicated, which is that formula, but still it's going to be doing a decimation by m. So the question is, how do we tell GNU Radio that we have m inputs for each output? GNU Radio needs to know that. The clue is in here where it says there are other base classes like basic block, decimator block, interpolator block, and we can look at the documentation. So if we search for decimation block GNU Radio, there is this documentation about types of blocks in the wiki. And then it says decimation, and it says the number of input items is a fixed multiple of the number of output items, which is what we want. And there's an example in C++. There is also an example in Python, which is similar to the example we have in the embedded Python block. And then we see by comparison with the template we have in here, we see that the things we need to change are this base class needs to be decim block. We need to have decim block in here, and we need to specify the decimation. So that's what we need to do. We need to set a decimator block in here rather than a sync block. This had sync block before because that means one input, one output. But that is not the case with the spectral kurtosis calculation we want to do. And then decim, I think it's called decim, yes, equal to the decimation rate, which is m. And that's as much as GNU Radio needs to know about the interface of a block to be able to call the work function here. So, okay, before writing the math, let me let me actually do something. Let me do print output items dot shape equals items dot shape input items dot shape input items dot shape. It is always a good idea to print these when we are not sure about the shapes of these. These are going to be matrices. So as to check, then this line is going to crash because it's trying to copy all the inputted items into the output. And there are more input items than output items because we have said to GNU Radio that this is going to decimate by a factor of 10, but it doesn't matter. So it will crash in here, but this will run. So let's see. I need to have something connected here. So I'm going to put a null sync. I don't know if I've used the null sync before. It discards the output. So we can, or the input of the null sync. So we can floating point NFFT, and then we can connect this. And this is useful for running tests because now we can run the flow graph and see what happens. So it's opening the RTL-SDR and we see this is stopped because there's a crash message here. Oh, there's no shape. Yeah, I've made a mistake. So what's the mistake? Block in GNU Radio can have multiple ports. Do I have an example here? No. So let's put an example. So add, for example, has 2 input ports and 1 output port. And there are blocks which can have many input ports, many output ports. How are those identified in Python? With these brackets. So input items, it's actually a list of things. Each of them corresponds to a port. Output items is also a list of things. Each of them corresponds to a port. So input item 0 means all the input items on port number 0, which in this case is the only port we have. Why do we only have 1 port? Because this is a list of ports and we only have 1 element. If we wanted multiple ports, we could add more elements to this list. So what I wanted to do was to put zeros in here, because otherwise that's a list and the list doesn't have a dot shape method. Once I have the element 0, that's all the input or output elements for port number 0, and that's a NumPy array, so it has this dot shape. Let's try to run this again. And it has stopped, but now we have our output. And it says the shape of the output is 1 and 4096. And that makes sense because we have 4096 FFT beans and we are requested to produce one of these spectral kurtosis calculations. The shape of the input is 10. We are given 10 different FFTs so as to produce one spectral kurtosis. Why? Because GNU Radio knows that we need 10 inputs for each output because we have said here. So it's actually going to adjust the sizes of things for us. This need not be 10. This could be any multiple of 10. For example, I don't know, 310. And then if we are given 310 FFTs, we need to produce 31 spectral kurtosis vectors. But we are always ensured that this is 10 times this number. Any questions so far? Okay, so let's move on to the math. I'm going to keep these prints for the moment. We will remove them later. And what I'm going to do is I'm going to say my input, I'm going to call it X. It's going to be input items 0, but I'm going to reshape. I'm going to save the FFT size in here. I'm also doing this to write less. Rather than typing always self.m, I'm going to assign it to a variable m, and then I'm going to reshape in this way. So this means something like this. This means however input size we have. For example, we could have had 310 and 4096. We are going to reshape that as something, maybe 31 times 10 times NFFT. Why? Because in each block of M, which is given by this dimension in the middle of the array, we are going to do the summations for the spectral kurtosis formula. This one represents the frequency dimension, and this one represents the number of block we are in, because this calculation is done in blocks of M FFTs. So this is my input, reshaped in a way that is easier to use. Something else I'm going to do as an optimization is you can see that the only thing we need is actually this xim modulus to the power 2, because then this to the power 4 is actually the same as to the power 2 and then squared. So I'm going to compute that. I'm going to call that z, and that's x dot real squared plus y dot real squared. There are many ways of computing the magnitude squared of a complex number. We could have even computed that in GNU Radio with a complex to magnitude squared block if we wanted, but we can do that in Python too, as in here. Okay, so now we are ready to write this spectral kurtosis formula. Can I maybe do something like this where I have the two windows at the same time? Yeah, this is fantastic. So I want to write this formula in Python. So let me see. Maybe I can do something like kurtosis equals this initial term is m divided by m minus 1. And then I need to multiply by all these thing in square brackets, which is a quotient, but that doesn't matter much because I mean this m plus 1 could go outside of the quotient. So I'm going to write m plus 1, then multiply it by what? By a sum. So I'm going to write numpy sum, and then we will decide exactly what we are summing. Then we have these things to the power 4, but we have computed already the power 2, so that is set. Then I need set squared. And I need to sum along the dimension here in the middle, because these are sums of m elements. So I'm summing across the axis 1. This will leave the number of blocks dimension and the frequency being dimensions untouched, and it will collapse things along the I equals 1, 2, 3, etc. m dimension by doing this summation. So this is the thing on the numerator. On the denominator, we have a similar summation. So that is the sum of z only. So we have z in here. Axis equals 1 also because we are summing m elements. And then we need to remember this needs to be squared. So like this. And finally, a minus 2, which comes here. Any questions? Maybe did I do any mistakes with the formula? I think not. Is this clear? Basically, this is the whole point of the exercise, to give you the means so that if you have a formula on some paper or an idea of how to write a formula, you can wrap that formula up as a Python block. Okay, so we have the kurtosis here, and then I think we can even write the kurtosis directly on the output, even though the shape is not the same. I think it will work, but let's try. And if it doesn't, we can reshape. Something else I need to mention, the output items. So these return length of output items. The work function in a block always needs to return how many output elements or output items it has produced. In this case, we are producing all of the available, uh, let's say, positions in the output buffer. But there might be other cases in which we cannot produce all of them because we need additional information. So we could decide to produce less output, and then we say to GNU Radio, in this work call, we have only produced, I don't know, 3 output items. But oftentimes this is going to be the length of the output items, meaning we have produced everything we could have produced. So that's it. Let's see if this runs or fails, because I'm not too confident on the final reshape. It doesn't run, and it says, oh, it says NFFT is not defined. So that's a different error because I need to use self NFFT. So since we are coding, it is possible to do many coding mistakes, and everyone does. But you can see that oftentimes the error you get in GNU Radio, it's a Python error, so it's very easy to trace back to the code. And it actually tells us line 35. So this blah, 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 line 35 means the line where the error happened. And this is line 35 on the text editor. So, okay, let's see if this works. No. And then now the error name y is not defined. Oh, where's y? Oh, in here it's actually x imaginary. Yeah, I think it's like that. So the input is called x, and then to compute the magnitude square, I'm doing x real squared plus x imaginary squared. That's what I meant to write. What else? So this is working, or maybe not. Okay, this is working, but it's actually not the best thing. So this is another pitfall. Since I have left these print statements, then this is printing a lot of information. GNU Radio is very bad. GNU Radio Companion, I mean, when you try to print a lot to the console, so it kind of freezes up. And then I basically need to kill it. So where is it? Where is GNU Radio Companion 1171768? Is that right? 1171768? Yes, I don't want to kill anything which is important. Oh no, the PID is here, sorry. So 78880. Let's see, will that work? Yes. Okay. So just remember when using your Radio Companion, try not to print out a lot of information to the terminal. If you want to print out a lot of information, you can run your Python script from the terminal rather than from within the GNU Radio Companion GUI window. That's the thing here. So let me see, not scripting, Python blocks. I want to open the flow graph I was working on. And to avoid any confusion, I'm going to close this. I'm going to open this in editor. I'm going to go back and then comment these two out. And then, okay, so we have something which is working, or at least it's not failing. We need to look at the output to see if it's implemented properly. So let me plot all of this and also maybe come up with a reasonable number of elements for M. So let's see, variables, time, integration. 1 second, as usual. Then M is going to be, if I want to do blocks of 1 second, I need to do the sample rate divided by NFFT. That's how many FFTs per second I have. What's going on here? Okay, approximately 781. So I need to round this to get an integer. Now I have 781, and this is my value for M, so I can enter it here, M. And we have spectral kurtosis using M as the integration factor or as the number of elements to be grouped in this formula. I can remove the null sink and then do a repeat. And this is because we only have 1 output per second. If we want to plot that in a vector GUI sync, then it's a good idea to repeat this by either 10 or 100 times to make the plot refresh faster. I have already explained this small technical detail. So, because otherwise the plot will keep waiting until it has enough inputs. It buffers a bunch of inputs, and we don't want that to happen. So Qt GUI vector sync is a plot for anything that is a vector, and we need to specify the vector size. Then what else? The x-axis is going to be the frequency in megahertz. So I need to have a starting value, which is the sample rate, divided by 2. That's the minimum frequency I have, which is minus 1.6 megahertz. But since I want in megahertz, I multiply by 10 to the power minus 6. So we actually get our 1.6 megahertz. And then the step value is how many megahertz per FFT bin I have. So that's the sample rate divided by NFFT. This is hertz. Is this correct? No. So we have 781 hertz per bin. If we want this in megahertz, then we multiply in the same way, and the y-axis is the spectral kurtosis. We can also label the plot as spectral kurtosis. And the x-axis units are megahertz. The y-axis units are nothing because kurtosis is adimensional. If you do dimensional analysis, you can see that everything is to the power 4, and so it cancels out. And let's see some reasonable values for this, maybe between -5 and 25 or something. So, okay, maybe 25 was too little. Maybe let's put 40. Yeah, still we have some things which go above the range, but we can zoom out like this. So I'm going to explain some more details about what we can see in the plots, but before doing that, any questions? Okay, so we can see the spectrum of the FM radio stations here. And in some parts of the spectrum, there is no radio station, so we have the noise floor. And as I mentioned, or as the paper mentioned, let me move this back here. If the signal is a Gaussian complex random variable, the spectral kurtosis is going to be 0. So in those parts of the spectrum, let me show it like this, where there are no FM signals, for example, in this region, we have a spectral kurtosis which is very close to 0. And maybe also in here and somewhere else. However, there are some FM stations, for example, this one, which are not so strong in the spectrum. You can see them, But if we calculate the spectral kurtosis, you can see, yes, there's something in there which is not at all Gaussian because it has a very large spectral kurtosis. So this is a way of detecting interference. You could say, if I want to observe something which is expected to be Gaussian noise, and most astronomical sources are, but I have some communication signals which are interfering, maybe these FM radio stations, I'm going to calculate the spectral kurtosis, set a threshold, and say everything which has spectral kurtosis greater than, I don't know, zero point 0.5 or something like that, I will remove it and not consider it in my calculation. So I would only be looking at this part of the spectrum, this part, this part, this part, and this part, and the rest would be ignored. So that's how spectral kurtosis can help us. Also, something else which is interesting to see for me, because I hadn't seen this effect before, is that for FM radio stations, you have like this U shape where the kurtosis is usually quite high on the edges of the signal, and it is low on the middle. So the middle looks more Gaussian than the edges, probably because of the slope of the signal. I don't know exactly why it happens, but it's interesting to see. And you can see occasionally there's some things popping up which might correspond to some interference. I can auto scale on this one, and you can see those. Any questions about the kurtosis for these signals? Okay, there are more things we can demonstrate with this kind of flow graph, because something else the paper said is, if we have a signal like this one, and this means it has a constant amplitude, it only occupies a single frequency, so that's the reason why there is this is the frequency domain representation, right? It says the DFT is something like this. So it occupies a single frequency and it has a constant phase, which is the same thing as saying my signal in the time domain is the same as a constant amplitude times a complex exponential of some frequency and some fixed phase. So basically a tone of constant frequency and amplitude. The spectral kurtosis should be -1. Can we demonstrate that with this flow graph? Well, we can tune to a different frequency, maybe 117 megahertz, where we have this aircraft navigation signal, that VOR station. And I think that if not ideal, maybe that's, yeah, that's close enough probably. So the value in here is minus 0.9 almost, and it's never going to be perfect. But you can see, because this is a signal of relatively constant amplitude and constant frequency, the spectral kurtosis comes out negative. Also in this interference we have in here, which is tiny, but in here it is quite visible. The sidebands on this signal as well, they are characterized here. So it's interesting. There are things which are easier to see on the kurtosis than on the waterfall, and we could look at other bands. So for example, 1090 is a fun one because this is where those aircraft signals are. And then you can see in the spectrum there isn't much, because the pulses are brief. So what happens is the total power is not so much. They don't have a large contribution to the spectrum. However, because the kurtosis is looking at the distribution of random variables, it will see that at some points the amplitude is very large because there is a pulse transmitted from the aircraft, and the rest of the time the amplitude is much lower. So we will see a large spectral kurtosis, and that's the reason we can see all these different frequencies. Those correspond to them. I already have it somewhere. Let me see, maybe Well, I can open another window like this. So the 1090 dataset, we saw that it has pulses at different frequencies, and they are not so easy to see in the spectrum or in the waterfall because they are quite brief. But when we do the spectral kurtosis, it is quite noticeable that there are like 4 different frequencies where they are, or maybe 5, where they are transmitted more frequently. Okay, any questions at this point? This is really all I had for today. We have finished slightly before the top of the hour, but I think that's good. You have good material in this tutorial. It's mainly intended for reference. If you want to do something similar in the future, you can always go to the GitHub in here and use the examples, modify them to your needs, and that already gives you a good starting point.